Okay, let's do section 3.6, graphing with calculus and with calculators. So as an introduction, recall that so far in this section, we've examined how the derivative of a function can be used to explore the graph of a function. We've used the first derivative and the second derivative, and knowledge of what those tell us about where the graph is increasing, decreasing, concave up, concave down, how those derivatives show us where maxima and minima are and where inflection points are to draw graphs of certain curves. I'm going to use this knowledge that we've talked about, but now I'm going to bring in either a computer or a calculator. So if you have a graphing calculator, you could do the same thing. And I'm going to use all of that to aid in graphing by comparing the picture of the graph that I get on the computer or a graphing calculator with our knowledge of what the derivative tells us. And the reason that we want to do this is because if I had to graph by hand all functions possible, I might run into some functions that are very, very difficult to deal with. But if I use computers or a calculator and I use derivatives, then I can tackle curves that would be really far too complicated to consider without the use of both of these. So we're looking at not well-behaved graphs in this section. I am primarily going to use Desmos for all the graphs that you will see in this section. I might pull up Desmos and show you a few things on that, but I'm primarily just going to take graphs that I've created on Desmos and input them into this lecture. But if you want to use Desmos for your purposes, you may. It is a free graphing program. Just go to that website. But if you are more comfortable with a different graphing program, feel free to use it. Okay, let's start with this example, and this is example 2 in your textbook. I want to draw the graph of the following function. Function is as follows: f of x is equal to x squared plus 7x plus 3 divided by x squared. This looks a little funny. Perhaps let me rewrite that. 7x. There we go. I want to graph that function in a viewing rectangle that contains all important features of the function. Important features being what are the maxes and mins, what are the intercepts, what are the maxes and mins, in other words, the extreme value intercepts, what are inflection points, what are asymptotes, those are the primary important features. I also want to estimate the maximum and minimum values and the intervals of concavity. And this is using the graph. This is by the graph. And then once I've estimated, I'm going to use calculus to find these quantities exactly. So that's my process for this particular problem. Okay. All right. This is the graph of the function f. I'll go ahead and label that. This is the function f of x. What could I possibly say about this? This is on the viewing window. It looks like my x's go from -8 to 8, and it looks like my y's go from -10 to 10. That's the current viewing window. I might make some initial observations here. What could I say about this? Let's see, y-intercepts. Does not look like there are any. Therefore, it appears that there is a vertical asymptote at the y-axis, which happens to be the line x equals 0. At least that's what it looks like from this particular graph and viewing window. X-intercepts. Looks like they occur, where do they occur? At about maybe 0.5. And then out here it may be 6.5. So x equals 0.5 and maybe negative 6.5-ish. What else could I say? It looks like there's probably a horizontal asymptote. So it looks like this graph has asymptotic behavior as it moves to the right and as it moves to the left. I don't know what that asymptote is. It's hard to tell from this viewing window. So I'll just go ahead and state there is a horizontal asymptote. There is likely a horizontal asymptote, and noting that this is a rational function, it's highly possible that there is one. That's a feature that occurs often in a rational function. What else could I say? I might be able to say, well, where are the mins and the maxes? Maybe I'll mark them on the graph. This looks like a relative minimum. A relative minimum looks like it's about at the point maybe it's a little less than, it's not quite 1, so maybe negative 0.9, maybe negative 3-ish. Looks like the approximate minimum. It doesn't look like there are any local max in this particular window. I might want to say, where's the graph increasing and decreasing? Let's see. It appears to be increasing here. Graph is increasing. Excuse me, it's decreasing there. What am I doing? The graph is increasing here on this interval from about 0.9 or negative 0.9 to 0 approximately, and it's decreasing everywhere else. So in that interval that I just noted, it is decreasing. It's going down from left to right. From 0 to infinity, it appears. And then it's also decreasing here from negative infinity to about negative 0.9. Okay, so I can make that note. I could also state, well, are there places where it appears the graph is concave up, concave down? It's definitely concave up here. Concave up in this same interval, 0 to infinity. On the left-hand side, it's a little bit harder to tell. It does look concave down here. Up over here, it appears to be concave up for that entire interval. And somewhere in here, the concavity changes. I don't know exactly where that location is. So let's just mark here to maybe about here. It looks like the graph is concave down. And maybe I'll put an approximate interval from negative infinity to about negative 1.5. And then in this interval here, from say negative 1.5 to 0, the graph is concave up. Which means there's an inflection point somewhere in there. There's a inflection point at approximately negative 1.5. Looks like the y value corresponding to that is what? Maybe negative 2.2 approximately. Those are all things that I could state from the graph. These are all approximate values, and I'll go ahead and note that. These are all approximate values. Approximate values. But they give us an idea of what I should find when I use the derivative to calculate these. There should only be one local extrema. There should be two intervals where the graph is decreasing, here and here. There should be two intervals where the graph is concave up, here and here, one where it's concave down. There should be one interval, one little bitty interval where it's increasing. There should be one inflection point. So now that we've got that, let's use calculus to find the exact values of these. I'm looking for this minimum. I'm looking for this value of the inflection point so that I can be able to exactly state these intervals. Okay? All right. So first of all, let's find the derivatives. F prime of x is equal to, well, let's see. You might recall that f of x is equal to x squared plus 7x plus 3 over x squared. I don't really like it written like that because then I would have to use quotient rule to calculate the derivative. So I'm going to rewrite it. This is x squared over x squared plus 7x over x squared plus 3 over x squared, which I can rewrite as 1 plus 7 over x plus 3 over x squared, or as 1 plus 7x to the negative 1 plus 3x to the negative 2 power. This is all just algebra that I did. I have done no calculus. This is all algebra. But now that I've done that, I can find the derivative much more easily. So on the left-hand side, f prime of x is equal to derivative of 1, which is 0, plus 7 times the derivative of x to the negative 1, which is negative x to the negative 2 power, plus 3 times the derivative of x to the negative 2 power, which is negative 2x to the negative third, which I can simplify. This is equal to negative 7 over x squared. Actually, let me not write it like that. Let's write it as negative 7x to the negative 2 power minus 6x to the negative third power. And the reason why I'm writing it like that is because I want to now take the second derivative. F prime prime of x is equal to the derivative of the first derivative. So negative 7 times negative 2x to the negative third minus 6 times negative 3x to the negative fourth, which is equal to 14x cubed plus 18x to the negative fourth. Okay? So now that I've got that, let's do this. I'm going to rewrite them. F prime of x is equal to, we said that it is equal to negative 7x to the negative 2 power minus 6x to the negative third. Well, I could rewrite that as negative 7 over x squared minus 6 over x cubed, which if I want to put them over a common denominator, I'm going to multiply the first term by x over x. So that gives me negative 7x minus 6 over x cubed. Second, f prime prime of x, we said that it is equal to 14x cubed minus 18x to the negative fourth. I'm not going to go through the algebraic steps, but I know that I could rewrite it in a very similar manner as I did the one above, as 14x plus 18 over x to the fourth, which I'm actually going to factor. This is equal to 2 times x, it's 7x. 7x plus 9 over x to the fourth. I'll just factor it out of 2 from the top. Okay, so I have those derivatives. I want to figure out, first of all, where are possible minima and maxima. So where are the critical points? Where is the first derivative equal to 0? This occurs where this first derivative is equal to 0 or that doesn't exist. In other words, where it, not where it doesn't exist. This occurs when this is equal to 0. In other words, where the top is equal to 0. So I'm going to set the top, negative 7x minus 6 equal to 0, and I will solve for x. Add 6 to both sides. I get that negative 7x is equal to 6. Divide by negative 7. I get that x is equal to 6/7. So that is a critical point, probably that location of the minimum. Places where that first derivative does not exist. Well, this is where the denominator of the first derivative is equal to 0. That occurs when x is equal to 0. So I have two locations now where that the minimum could occur. Two locations where the sign of the derivative could change. I'm also going to find locations where the second derivative does not exist and where the second derivative is equal to 0. Remembering that the second derivative is equal to 2 times 7x plus 9 over x to the fourth. Places where the second derivative is equal to 0. Excuse me. The second derivative is equal to 0. These are locations where the top, 2 times 7x plus 9 is equal to 0. So divide both sides by 2. I get that 7x plus 9 is equal to 0. Solving that, I get that x is equal to negative 9/7 as my possible inflection point. And then places where that second derivative is equal to 0, or does not exist, excuse me, where it does not exist. These are the locations where the denominator is equal to 0, i.e. where x is equal to 0. So I have two locations where the inflection points could occur. Okay, I've got that. One other feature I might want to look at is there looks to be asymptotes in this function. I should examine them. Let's look at asymptotes. I'm going to figure out, well, is there a horizontal asymptote? It looked like there was, but I didn't know where. Remember that f of x, we simplify it as 1 plus 7 over x plus 3 over x squared. So to find horizontal asymptotes, I'm going to find the limit as x approaches infinity of that function 1 plus 7 over x plus 3 over x squared. This is equal to, well, the limit of 1 as x approaches infinity is just 1. The limit of 7 over x as x approaches infinity is 0. And the limit of 3 over x squared as x approaches infinity is 0. So this is equal to 1. So it appears that this graph has a horizontal asymptote at y equals 1. At y equals 1. You could find similarly, the limit as x approaches negative infinity of that function 1 plus 7 over x plus 3 over x squared is also equal to 1. They're the same in this case. So there is the horizontal asymptote. Y equals 1, we found the exact value. How about vertical asymptotes? Vertical asymptotes. Well, this one was actually pretty clear from the graph. We also could tell from the function that x equals 0, the y-axis, is the horizontal asymptote, the vertical asymptote, excuse me. The vertical asymptote. Okay. Now let's look at our function again, our graph, I should say. Remember, this was our graph. We said that there was a minimum here. And that minimum we said was about negative 1, or about negative 0.9, so a little less than 1. Oh, I made a mistake, didn't I? Remember our critical points? We found correct. I said x equals 6/7. It was actually x equals negative 6/7. I made an algebraic error there. X equals 0 was another. The possible inflection points we found occurred at x equals, what was it? X equals negative 9/7 and x equals 0. Okay, so this x equals negative 6/7 has to be this point here. It's the only place that a minimum can occur. At x equals 0, I have this asymptote, so a minimum certainly cannot occur there. So I know this minimum value. This point is negative 6/7, and then if I put negative 6/7 into the function, I'm going to get negative 37/12. That is the exact value of that minimum. I also know the inflection point. The inflection point is here, negative 9/7, which is approximately negative 1.44. That's right here. This is the inflection point we found before. It's negative 9/7, and then I can put negative 9/7 into my original function and find a y value of negative 71/27. Okay. I have a horizontal asymptote at 1. I can put that on my graph. Horizontal asymptote at y equals 1. I can go ahead and put that here. And I can see over here on the left that this function does just kind of creep above the x-axis in this particular viewing window. So I could have guessed from that that the x-axis was probably not an asymptote. Wasn't necessarily the case, but y equals 1 makes sense in this case. I can say that there's a vertical asymptote at x equals 0. This axis here. I'll go ahead and put that on there. And what could I say about the derivatives? So I could say that the sign of the first derivative can only change. Where could it change? It can change here at the minimum. and it can change here at this asymptote. Those are the locations of the critical points we found. So I could say that f prime of x is negative in this interval from 0 to negative 9/7. So I could say that the graph is increasing. It is increasing, excuse me, it's decreasing, I think I did that last time. Decreasing in this interval from negative infinity to negative 6/7. It is increasing in this interval from negative 6/7 to 0, and it is decreasing. The sign of the first derivative is negative in this interval from 0 to infinity. I could also say that the graph is concave down. Concave down. I could say exactly where now. It's in this interval from negative infinity to negative 9/7. Negative 9/7. I know outside of this window it does not change, because the only locations where the sign of that second derivative can change were at these two values. I could say that the graph is concave up in this interval from negative 9/7 to 0, and it changes at 0. And I could say the graph is concave down in this interval from 0 to infinity. My algebra showed me, or my calculus rather, with algebraic applications, showed me that these are the only locations where that concavity can change. There are none outside this viewing window. This is the only location where the increasing, decreasing nature can change, here and at 0. There are none outside of this window. And I know exactly where my isotopes are. There are none outside of this window.